So let me welcome you to today's DTP Colloquium. You might be surprised why I'm here. Part of the reason is Rishi is away, so I am filling in his place. In any case, let me remind you that the today's Colloquium is special. Part of the reason is that it is continuation of the DP Roy Memorial Lecture. The first part, the public lecture which you heard yesterday, that was basically for not technical, not for specialists, but today it's supposed to be focused towards us mostly. Okay, so without much delay, I leave the floor for Professor Godbole. Rohini.
Okay, thank you very much, and pleasure to see all you again. So without much ado, let me share my screen, and I hope people can see my screen and
Yes,
full screen. Okay, so we will begin. As I repeat, as I said yesterday, it's indeed a great honor and pleasure to give a talk as a deep part of the DP Memorial Lectures. Having been a collaborator and friend of DP for decades, this is a very pleasant duty to remember him. And not surprisingly, the subject that I have chosen, I will, even in the course of work talk, I will perhaps refer to some of the very old work that we did together. So what I want to discuss today is basically, the title is ElectroWeak SUSY at LHC. HL is high luminosity LHC. It should have been LHC, sorry, it's typed HLC. And I would in particular focus on two specific topics. One is a very low mass, lightest supersymmetric particle, and the other is a heavy Higgs, supersymmetric Higgs. What is light and what is heavy shall become clear as we go along. As I said, this is indeed part of DP Roy Memorial Lecture. So I will begin my talk by giving a very small introduction. Then I will sort of try to motivate a low mass dark matter in supersymmetry, or rather cover the current situation about what is a low mass. And for me, low mass is the lightest supersymmetric particle, which is lighter than the light Higgs, thus Higgs that we have discovered 10 years ago. And then I will refer to I will refer to two types of light supersymmetric particle. One is a neutralino, and that in the context of specific supersymmetric models, that is the phenomenological minimal supersymmetric standard model and next to minimal supersymmetric standard model. Here I will refer to a fair amount of personal work. Then I will also cover the case of a right-handed neutrino, which I will maybe give you an overview of some discussions that exist in the literature about in the constrained minimal supersymmetric standard model or phenomenological supersymmetric standard model, and also the next to minimal supersymmetric standard model. And then I would, the second part of the last part very briefly, I will cover the heavy Higgs with emphasis on supersymmetric Higgs, of course, with emphasis on ElectroWeakino final states. This is actually based on a fair amount of work that we have been doing in the last 4 or 5 years with a team, with my old-time collaborator, Genevieve Belanger, and as well as students and my young colleague, Biplab Bhattacharya, and his students, as well as another young colleague, Suchita Kulkarni, who works in University of Graz. And in a sense, though this is the work that we did on the subject over the last period of last 5-6 years, this is actually almost an analytical continuation of the work that we had been doing for about 10 to 15 years. And so this is an area, particularly the low mass neutralino, that I have been kind of visiting on and off for last 20 odd years. In fact, most of us grew up in the period where supersymmetry was actually the standard beyond standard model scenario. And the lightest supersymmetric particle was the most attractive, weakly interacting massive particle as the candidate for the dark matter. And the audience here have seen the names, and nobody requires an introduction as to what are the reasons why we found particle physicists found supersymmetry attractive. But what some of them, like people like Shomen, may not know in detail is that the Large Hadron Collider results actually put the idea of what we call natural SUSY under a lot of stress. And the xenon one-ton results that have come from the direct detection experiments of dark matter have actually put the paradigm of weakly interacting massive particle as a dark matter candidate actually under quite a lot of stress. And, as we know very well, over the last 10 years again, the Large Hadron Collider has been running very successfully. And many of our own colleagues from TIFR have been involved in the analysis quite often of the supersymmetric searches. Unfortunately, these searches have only constrained and put lower limits on the masses of various particles, the gluinos, the squarks, the MSSM Higgses, the ElectroWeakinos, which are nothing but the supersymmetric partners of electroweak bosons, either spin 0 Higgses or spin half, spin 1 Z and W. Now, all of these mass limits actually are constraints because they're not simple mass limits. Many of them, all of them actually translate into constraints on parameters of the supersymmetric models. And therefore, now many of the parameters of the supersymmetric theory actually have been constrained to have very, very high values. And by very high values, I mean values beyond, 1 TeV or 1.5 to 2 TeV. But one supersymmetric particle that is still allowed to be lightish, that is the lightest neutralino, LSP, and that's the Kaiwan knot twiddle. And this is really in the minimal supersymmetric standard model. This is a somewhat oldish slide of lower limits on the masses of these particles. And these are all the limits. I've taken this actually from the PDG, and there must be improved sort of changes or further stricter limits as they have gone. The limits have gone up, but not by too much. And I don't want anybody to read it. But what I found more interesting, and unfortunately the experimentalists have stopped giving us these kinds of limits, and now we have to do our own work to get this. But what this is that these limits on the masses, as I said, have to be translated into a particular model on the restrictions on the parameters. And then what these people have done in Atlas was they had translated all these limits. You had to translate them in the framework of a given model. And once you translate them, what they had shown is that in how many percents of the models that particular point remained excluded. And here, for example, a mass value of, let's say here as an example, a mass value of here was 250 GeV was excluded in almost all the models that they considered. But then by the time they came to a mass of 600, 700 GeV, that was excluded only in about 50% of the models. So if you just want to, I will not be able to show you in detail, but this limit on stop, which here is only, let's say, only 600 or 500 GeV, in that blue plot, it would be much more. So if you look at that, then the limit on the lightest neutralino is actually found that even the mass value of 100 GeV is allowed in more than 50% of the model, because only about 50% of the models are excluded. And if you go to a mass value of 400 GeV, even more models are allowed. So that is the statement that I made, that a small mass neutralino, and by small here, I mean anything from above 100, because here, this is only 50% of the models were excluded. low mass neutralino is still very much allowed in the phenomenological minimal supersymmetric standard model. In the framework of a specific model, and this is an analysis from John Ellis and his collaborators, what is called the master code, they also give similar limits. Again, I don't want you to read them, but what they do is that since they are working in a very specific, well-defined model, they also find what is the best fit point and what is the 95% confidence level where they think the LSP will exist. And their best fit LSP actually has a mass of a few hundred GeV. So there is basically this wide range of LSP masses that the data still allow. So what are the real numbers? So let me give you the summary of the run to data after 35 from to 1 inverse. And here, supersymmetric partner of Higgses, which is that is a LSP, lightest supersymmetric particle, which is a partner, super partner of a Higgs, which we call higgseino. A pure higgseino at up to a mass limit of about 390 GeV has been ruled out by these data. And a pure Vino-like neutralino, that means which is a supersymmetric partner of W. What this particularly means that this spin half dark matter particle has exactly the same couplings with matter that a W has. Similarly, a higgseino would mean exactly this, that it's supersymmetric, is a supersymmetric partner of one of the Higgses, and the couplings with the matter would be exactly what the Higgs would have with the standard model particles. This is really the reason for, because this is supersymmetric. Now, a pure Vino up to about 650 GeV is ruled out. A pure higgseino up to 390 GeV is ruled out. But what we wanted to do, and some of us have been doing this, is can we critically evaluate the case of a light LSP, because this is a limit for a pure higgseino, but nobody tells you that the supersymmetric parameters would be such that the lightest supersymmetric particle will be a pure higgseino. So therefore, in the context of a particular model, what are the limits on the higgseino, on a lightest neutralino, and what are then the search strategies or search chances of these lightest neutralinos at the next run of the Large Hadron Collider, which is going to be starting soon, the high luminosity run. So the subject of my talk therefore is a light LSP. I'm going to focus on a light LSP such that twice the mass of the neutralino is less than the Higgs mass. And I have tried to argue that such a low mass neutralino is very much still allowed. And now we want to know how much. And that's what we are going to discuss in more detail. And then phenomenology of how search strategies for a heavy Higgs which decays into ElectroWeakinos. This is what we want to do. For fun, I want to show you that the light ElectroWeakinos have been a matter of great interest and great investigations from a very, very long time. In fact, I reproduce here the abstract of a physical revelators paper from 1983, which from Steven Weinberg, which said that a large class of broken supersymmetric theories is shown to imply the existence of the fermions, lambda plus minus and lambda naught. These are indeed the Vinos that I talked about, the lighter than or nearly degenerate with the W plus minus and the Z0 gauge bosons, and with vanishing baryon and lepton number. So if lambda plus minus is appreciably lighter than the W plus minus, he was suggesting that it could be searched in W plus minus decay. Indeed, I remember that this paper was responsible for one of my own earliest papers in SUSY, where we looked at the decays of the W and the Z into ElectroWeakinos in the context of the data from Fermilab Collider. Of course, now there is a lot of water under the bridge since then, and we know that at least the simplest Vino, which is lighter than the W, does not exist, because now we have LHC telling us this strong constraint. All right. So now why are we thinking about this? The small mass of the observed Higgs actually smells like SUSY. But however, its mass very close to the upper limit of 132 GeV in a minimal supersymmetric standard model also tells us that the SUSY breaking scale is rather large. For many people, this indicates unnaturalness. And for example, one can go to Dine and many other articles which discusses whether naturalness is under stress, and many people believe it is in stress. However, my friend Alexis Tata and his collaborators actually they designed a particular measure of naturalness, which, their philosophy was that the measures of naturalness which we are constructing have high values because we are missing correlation among the parameters of the supersymmetric models, which actually can make the values of the measures small, even if the particle spectrum and the particle masses at the electroweak scale are the same. And this was a paper they had in 2013. And therefore, they constructed a measure, what they call delta electroweak, which is, of course, constructed out of the loop-corrected values of the parameters of the SUSY model at the electroweak scale. And if those are large, they said this will definitely point towards losing naturalness. And what they showed is that you could have large, and by large, I mean here 1.5 to 2 TeV gluino masses, and have smallish stop masses of the order of 700 to 800 GeV. In this case, the LSPs are almost always Higgsinos, and the masses are around electroweak scale, and that's 320 GeV. So right now, the limit there is 320 GeV. So what this is telling you is that we should be looking at the small mass electroweakinos, even in the context of naturalness, with a lot of interest. We should peer at it with our lens. And in a few years after that, my few friends from Netherlands had actually seen that a light electroweak sector is actually natural in the sense of Alexis Tata and company. And what they had shown is that and the lightest supersymmetric particle having a mass somewhere between 30 and 40 GeV actually corresponds to a rather small value of delta electroweak, because light here means that delta electroweak is 4, and as you go to dark, it varies from 4 to 10. And even then, here the measure is rather small. That is, 10 is equivalent to like 10%, which is still not so bad. So therefore, what I'm trying to tell you is that LSP, which is light, is even from naturalness consideration, somewhat modified naturalness consideration, is very much alive. And therefore, phenomenologically, what happens is something we must see. So what are the candidates in supersymmetry for lightest supersymmetric particles?
Some Russian Prof. I told him I don't want to do it.
Excuse me?
No.
Excuse me? Should I continue?
Please do. I think somebody's,
Yeah, okay. All right. So 1 minute, I lost.
Is there a question?
Yeah.
I don't think there's a question.
Then I will just continue.
Sorry.
So the gravitino I won't even discuss. And there is another one which is supersymmetric partner of the neutrino, that is neutrino, and it cannot be the dark matter for observational reasons. So what I will do is that I will focus on the most popular case of neutralino being the lightest supersymmetric particle. And the mass and the couplings of this lightest supersymmetric particle, or in general, all the neutralinos, of course, depend on PMSSM. And I have tried to argue to you that the weakest LHC constraints are on the mass of the lightest neutralino. The weakest, also theoretically, a light LSP from the naturalness consideration is still sort of very much allowed. And therefore, this is something that we want to investigate. So the questions we want to ask are that how light a chi-1 knot will be and still a viable dark matter candidate. Now, what is meant by viable dark matter candidate? Of course, only two things. One is that it should provide the correct relic density. That means it should not overclose the universe. The relic should not be bigger than the observed relic density. Otherwise, the universe would not be the way we see it. So that is the point. And it should satisfy the direct or indirect detection constraints. So what are these experiments? So let me just remind you of the relic density, that the measurements by CMB measurements by the Planck satellite and the anisotropies in the cosmic microwave background radiation actually tell us that the dark matter density omega dm times the reduced Hubble constant square is really now quite accurately measured, 0.120 plus minus 0.001. And in a model, one can predict this relic. And this predicted relic in a model using cosmology, understanding of our early cosmology, we know that this can be is predicted to be 3 into 10 to the minus 27 centimeter cube per second. Sorry, actually centimeters. Yeah, it's correct. Centimeter cube per second divided by the annihilation cross section of the dark neutralinos times the velocity and averaged over velocities of the dark matter itself, because there is a certain velocity profile. So the couplings of the dark matter particle which decide the annihilation cross section will actually then decide the relic density, and this couplings will actually depend on the model. So very roughly, a dimensional argument, sigma annihilation will be simply g chi twiddle fourth divided by m chi twiddle square, and therefore the measured relic that is here actually will produce constraints on this combination. This is actually very simple-minded, and the actual calculations are sometimes more complicated. And this expression that I've given you is for a thermal relic. That means that the species abundance in the early universe is really decided by the temperature at which that is the relic abundance is decided by the temperature at which that particular species falls out of thermal equilibrium with radiation and other particles present in the plasma. And that means that it freezes out, and that's the thermal freeze out, as we call it. Now, the formula that I gave you is an approximate one. One has neglected the velocity dependence of the annihilation cross section here, and there are some serious implications of that velocity dependence. So for the observed relic density, which is 0.120 plus minus 0.001, one can actually see that the freeze out temperature for the dark matter particle here is actually something like in the range of m chi twiddle by 30 to m chi twiddle by 20. And that means that this chi twiddle has to be moving at non-relativistic speeds at the freeze out temperature, and hence what is preferred by this rather simple understanding is what is preferred cosmologically is a cold dark matter candidate. Now you can also expand this annihilation cross section as a function of the velocity, and for the S annihilation of the Dirac fermions, the leading term is independent of velocity, and for the Majorana fermions, like they are in supersymmetry, the leading term actually is proportional to V, and therefore, as you can imagine, the regions of the couplings which give rise for a given mass, what would be the relic density really changes very much depending on whether you have Dirac fermions or whether you have chi twiddle fermions. And more important than that, the really thing that it affects is the cross sections at the freeze out, and what the cross sections now are very different because the velocities change at the early universe at the freeze out and are substantially different now in the current universe. And that's why this issue is kind of very important. And for resonant annihilation, there are additional complications. I will not go into that. So in the usual scenario, when we calculate this thermal density, we actually assume that the expansion of the universe is adiabatic. And if there is a entropy injection, for example, decay of a heavier particle, like a heavy modulus in string theories, then one can actually dilute the relic density of a species because there is more entropy injection. And what we really calculate is the ratio of the number density to entropy density. And that's what we then finally translate into the mass density. So therefore, one can actually think of various other possibilities which will give us the relic density, even if the calculation of this particular calculation by using sigma annihilation that the model predicts gives a much higher number. It is possible to still get the right relic, and that happens in two different ways. One is called freeze-in, and in this freeze-in, what happens is that instead of having a freeze-out mechanism, in this case, what happens is that we are actually getting the dark matter generated by the decay of other degrees of freedom, and that the decay width and the mass of the ith BSM particle, if it is gamma, its decay width is gamma I, and mi is its mass. And if their decay gives rise to the dark matter particle, then we can again compute the freeze-in density, and then it's a function of these additional parameters, the masses of DSM particles. This is not necessarily, it can be, need not be, but it is in some SUSY that is augmented, where there are additional particles which give rise to the neutralinos in the process. There is also something called out of equilibrium decay of an LSP. This is realized in SUSY quite often. And this is when the next to lightest supersymmetric particles decays on a very long time scale. And this can happen either due to compressed spectra, or it can happen due to small couplings of the MLSP. And then the NLSP decays into a final state, which is contains the LSP. And therefore, there is additional thermal density, that is the additional relic density that is created even by the decay of the NLSP. And in this case, even if the relic density as computed from this formula is actually not enough to produce the relic of the right size, indeed, the out of equilibrium decay of the NLSP can give rise later on to the appropriate relic density. And in fact, this plot that I have taken from a review by Bhupal Dev, Anupam Mujumdar, actually you can see that this is the equilibrium abundance of a particular species, and this is in the freeze out mechanism. And depending on the annihilation cross section, what the value is, you can actually get various different relic density. And this is the freeze in, where you start with low density of the dark matter, and then it slowly grows. And again, depending on the cross sections that you have, you would reach the correct relic or not, depending on your model. All right. So now how do you detect this dark matter? And that is the supersymmetric LSP. One, of course, detects it in deep underground experiments. The indirect detection, which happens via dark matter annihilation in areas where the dark matter local density is very large, and that is in the center of galaxies or center of dwarf spheroidal galaxies, and so on and so forth. And remember that the annihilation happens to produce the relic in the early universe. And now in the galaxies, for indirect detection, the velocities of the dark matter candidate are actually quite different. And therefore, the sigma annihilation V average at the freeze out and at the present epoch are very different. And therefore, it depends on the velocity dependence of the annihilation cross section. That's why I pointed out to you that in SUSY, specifically, having a Majorana particle has an implication for this velocity dependence. And in addition to that, this velocity dependence is also complicated when annihilation of the dark matter in the early universe or even in today in the indirect detection happens through resonance. Then also a fourth point, which will be of relevance when I discuss the results we get, is that the direct detection cross-section for a pseudoscalar mediated process is suppressed much more compared to the scalar of the same interaction strength. So let us remember these four rules of thumbs. So now what is the story with the actual detection experiments? There have been some reported low mass lightest supersymmetric particle direct detections, but looks like that most of the reports are either due to experimental fluctuation or they are not dark matter. There might be astrophysical explanations. For indirect detection, there have been some again reports of detection, but there is a lack of clarity due to uncertainties with astrophysics. And the third is the direct detection, and that has improved by leaps and bounds in the past 2 decades. And the current status and the best limits from the direct detection, unfortunately, just like LHC, the direct detection has only limits. And what these experiments tell us, that if there is a WIMP, if there is a lightest supersymmetric particle as a dark matter, the direct detection experiments only have put an upper limit on the cross section that they can have with a nucleon. So this is the amount of experimental information that's available to us. Is there a cosmological limit on how light a CDM particle can be? And this actually was analyzed by Céline Bohm and Joe Silk, and then also a fair number of collaborators. And by using the Planck measurements on the effective number of degrees of freedom that is the effective number of neutrino species in the early universe, they were able to say that the masses of CDM as small as 2.5 MeV will be allowed. So there is no real limit from cosmology as it stands. Now the relic density calculus. Now let me just summarize what is the case with SUSY. In SUSY, the relic density calculations and the dark matter detection cross sections both depend on the couplings of the dark matter with the standard model particles. And in supersymmetry, the couplings of the dark matter with the standard model particles are given to us by supersymmetry. That means that, for example, in PMSSM, the chi-1 twiddle is a mixture of higsinos and gauginos. And in NMSSM, it's a mixture of higsinos, gauginos, as well as the partner of a singlet Higgs that exists in the NMSSM. And in the case of NMSSM, even the scalars are mixture of standard model singlet and a standard model doublet. So obviously, it means that the couplings of this chi-1 twiddle with the Higgses in NMSSM with the NMSSM Higgses, they all are decided by the extent of the mixing between the higsinos and the gauginos, that is the supersymmetric partners of the Higgses and the supersymmetric partners of the electroweak gauge bosons. And therefore, the extent of this mixing between different sectors actually decides what are the couplings of the chi-1 twiddle with matter and with the Higgs boson. So fine. So now some rules of thumbs again, that a Vino-like or a Higgsino-like chi-1 twiddle will really have to be heavy to explain the observed relic. Now, how in a particular supersymmetric model we will ever get a Vino-like LSP is actually a different question. Models don't particularly produce that very easily, but models do produce a Higgsino-like LSP rather easily, and that is the one that Tata's and company had pointed out to us. The models actually very often like a Bino-like neutralino, but a light Bino-like neutralino actually produces, because of its low level of cross-section, and remember the relic is inversely proportional to the annihilation cross-section. So because the Bino-like chi-1 twiddle has large couplings, rather small couplings, its annihilation cross-section becomes smaller, and therefore the basic freeze-out density that will be predicted by a Bino-like neutralino will be very high. So that will not be allowed by the measurements of the relic density. And then one will have to provide in the model for additional annihilation channels so that we can increase the annihilation cross-section. And that can be done by having a T-channel light slept on in the annihilation of the dark matter candidates, which is annihilation which is mediated by a light slept on, or a resonant annihilation via the Higgses, or that is the scalar Higgs or the pseudoscalar Higgs of MSSM, or the gauge boson Z. Now the Z exchange actually, again, because of supersymmetry, requires a non-trivial Higgsino fraction in the neutralino, and you need, so therefore now you need a neutralino which is a Bino-Higgsino combination, so that the combination Bino-Higgsino combination will give you additional annihilation channels through the Z as well as through the Higgs and increase the cross section. And this is sort of technically called the well-tempered neutralino. Now, for early days in CMSSM, the Leb constraint, and when I'm saying early days, I'm talking of 1990. And the Leb constraint on the chargino masses and the universal gaugino mass would have ruled out a light neutralino that is of 45 GeV or less, actually almost out of hand. So therefore, people concluded that a light neutralino necessarily means non-universal gaugino masses. And this is actually what we advocated in 1995 to 2000. Now, till that time, the dark matter detection experiments had not really come into full swing in action, and therefore these collider bounds that we had been discussing dominated the story. And we asked, now today the situation has changed. I have already shown you how strong the dark matter detection experiments have done. Well, they have done. And the LHC experiments also have ruled out many things. So now the question that we asked ourselves, how low a mass can a viable dark matter candidate have in SUSY, which is consistent with all the current exclusions? And can the future colliders probe these lightest supersymmetric particles? That is, can one do something with collider experiments? And there we wanted to use phenomenology of the heavier electroweakinos. And then the second question we actually had, which I will not go in much detail, but that is a kind of a question that we want to ask, is that can the models and observed relic density support a light SUSY dark matter particle if it is reported tomorrow in either direct or indirect detection experiments? And if that happens, what can the LHC, the HL-LHC, HE-LHC, or the E+E- experiment say about it? And why is it possible for us to ask such a comprehensive question? Is because the predictions for relic density, predictions for direct indirect detection, and the predictions for LHC phenomenology, everything is controlled by the same 4 parameters. And that is the beauty, that you can try to look at all the 4 issues. So we would look at PMSSM, the phenomenological minimal supersymmetric standard model. It is the extension of the standard model to include supersymmetry, and the parameters of the minimal supersymmetric standard model that affect the phenomenology of the lightest neutralino are actually only the mixing. I would not go and explain all the parameters, but mu is the Higgsino mass parameter. M1, M2 are the masses of the U1 gaugino. M2 is the mass of the U2 gaugino, and tangent meta is the ratio of the vacuum expectation value of the 2 Higgses. And the radiative corrections actually bring in an additional dependence on the triple coupling of the involving top, as well as the mass of the top, and sometimes even a dependency on the gluino mass. And I will try to discuss this in the context of standard and non-standard cosmology, which I have already touched upon. NMSSM contains an additional singlet Higgs superfield. So in addition to the above parameters, mu, M1, M2, and tangent beta, it actually requires few more parameters, and that additional singlet field actually gives rise to additional parameters. And there are also additional pseudoscalars and scalars. And those 4 parameters, kappa, lambda, A kappa, and A lambda, control the masses of the scalars and pseudoscalars, as well as the coupling of the neutralinos with the standard model particles. Then I would try to very briefly tell you about PMSSM and NMSSM with a supersymmetric partner of neutrino. So now we sort of start talking about the actual analysis that we have done. So till the dark matter detection experiments came in full swing, as I said, the collider bounds had actually dominated the story. And at that time, people had kind of said that before the xenon Munton and the latest LHC results came, people had kind of said in 2011, this is just before the LHC came up, that there is a lower limit on the mass of the lightest neutralino of 30 GeV in the phenomenological minimal supersymmetric model. So now the question is, we have much more precise determination of the relic density. We have very strong constraints from the strong direct detection compared to 2011, as well as much more measurements from LHC. There is also Higgs detection itself and the precision calculation of the Higgs mass. So the question was, how does this 30 GeV limit in the PMSSM get affected, and what does it look like in this newer analysis? Maybe I'll come back to that slide a little later. So this is, as I already mentioned, that we want to get the right relic, we need it to be a Higgsino-Bino mixture. But what it means is that if the Higgs lightest neutralino is a mixture of a supersymmetric partner of the B gauge boson, and that is the U1 gauge boson and the Higgs boson, then actually the Higgs can have appreciable branching fractions into an invisible neutralino pair. So therefore, you can actually study the invisible decay of the Higgs at the LHC, and therefore this invisible decay at the LHC actually will also constrain the light mass neutralino, which was not available. These data were not available in 2011 clearly. So this is the, as I said, I mentioned that I would mention one of the work that I did with PP, perhaps among the last ones, perhaps not really the last one, was actually about this invisible decay of the Higgs in the context of supersymmetry. So now for the invisible branching ratio, the current base limits are about 13% or 11%. It's a little bit better perhaps than 13, it's 11 most likely. And the future for looking for this dark Higgs is actually very, very bright. Large Hadron Collider will be able to look for invisible branching ratio to about 3.8%, and the International Linear Collider or FCCEE or CLIC can reach much smaller invisible branching ratios. Okay. So I will actually go and say that this I will try to not discuss, because this refers to the LHC constraints that already have, and therefore why those methods have no implications. So let me now try to tell you what are the ways in which one can, which searches which will impact the mass of the lightest neutralino. One is the invisible decaying Higgs through, let's say, so you look at PP going to HZ and the Higgs decays invisibly. So what you see is a mono Z, and that is the actually a very important and perhaps the best limit that we have got on the invisible Higgs is actually through this HZ, as well as the vector boson fusion of a Higgs and Higgs decaying into neutralino. So this, as well as this, the first and the third process have given very strong constraints on the invisibly decaying Higgs, and they will impact our analysis. And the second one is the direct production of ElectroWeakino states and their decays, which have been analyzed in the last runs of the LHC. So we are going to look at the constraints on the supersymmetric parameter space because of these two results from the LHC. That's what we did. And we looked at, because we wanted a mixed Bino-Higgsino light neutralino, we actually decided and focused in while looking at the parameters. There is a whole lot of parameters you need not remember or take their notice, but I would like you to notice this parameter M1. We have chosen this parameter M1 to be a light parameter, as well as our M2 is allowed to be large, but the mu is actually rather small. So we have large small m1 and small mu, and that actually gives you a light neutralino, which has a Bino-Higgsino mixture. So this is what we do now is that we consider parameter space, a point in this parameter space, and then we say that make sure that this point is allowed by all the LHC constraints on the supersymmetric parameters, particle searches, and we already have chosen the range of parameters such that we are we will not lose too many points in our constraints by non-observation of stop and non-observation of Gluino, etc. And then the constraints which come from flavor constraints come from the B physics sector, Higgs sector constraints, that is the mass of the Higgs, produce the correct mass of the Higgs. Then we calculate the invisible branching ratio for each point, and then we calculate the expected direct detection cross section. I told you that this direct detection cross section will also depend on the couplings, as well as the invisible branching ratio will depend on the couplings of this neutralino with standard model particles, and the relic density will also depend on the same couplings. And then we calculate all these things, and then we calculate the freeze out relic density using the very accurate programs, not the approximate formula. And then we calculate ratio of the calculated density to the observed density. And if Xi is less than 1, then it is indeed a thermal dark matter, because that's allowed. Then if it is much less than 1, we will need to think of an additional dark matter candidate. But if it is otherwise, this is it's either less. If it is 1, then we don't need additional dark matter candidate. If Xi is greater than 1, that is non-thermal, then we assume that there is a mechanism which will reduce the density to observed omega dm by entropy injection, by decays of moduli and what have you. So this was something we did 4-5 years ago. And at that time, the direct detection experiments were really not in good shape. And we, the gray indicates the entire number of points that we had scanned. And what is plotted is the invisible branching ratio of the Higgs as a function of the neutralino mass. And at that time, the best constraints from LHC on the light neutralino really came from Higgs to neutralino invisible decay width. And at that time, this upper line here was the constraints at that time, actually, and that all the other points were allowed. And if we have LHC, it was a little above, it was the LHC limit that it's possible at the end of 300 inverse femtobarn is 8.4%. And there was very little difference between that and the indirect limit coming from the Higgs width. And then we said here, therefore, that all these points below this line are something that were still very much allowed. And then we looked at how many of them are allowed by different direct detection experiments and which one will be probed in the upcoming direct detection experiment. And we had said that these blue regions are the regions will be then probed in the direct detection experiments. So a few statements one already had got, that only that there existed now a lower limit on the neutralino masses, lightest neutralino masses in PMSSM, which was about 39 GeV. And the certain region around MZ by 2 and a lot of certain region around MH by 2 was indeed allowed, which means that in the direct detection experiment, in these regions, the direct detection cross section actually was small. At the same time, the annihilation cross sections were large, as a result of which the relic density constraints allowed these points. So this is where we are. Now the LHC run 2 data became available and Xenon 110 came with its results. And indeed, this old analysis that we had done, we had decided that let's see how many of the points of our old analysis are left. And then we found that after Xenon 110 constraints were employed, we actually found that very few points, allowed points, were left in the Xenon 110 region and very few in the Z funnel region, where the annihilation happens to the Z pole, and therefore we get the not too high relic density. And here the annihilation happens to the Higgs pole, and that is still allowed. That was the story. And this here we had restricted ourselves to positive mu, but the story actually seems to be different for negative mu, and we are currently investigating that. But in between, when we are investigating it, I might share those results at the end of my talk. But right now, let me tell you what we continued. Then we asked the question, can we study the production of the heavier electroweakino pairs for those points in the parameter space which lie here, which were allowed by all the constraints, and then ask the question how HLLHC will look for them. And the HLLHC will look for them through, I will not go again through the details, that's a matter of phenomenological details of the analysis, but we actually figured out which will be the interesting final states where these heavy electroweakino pairs would decay, and how one can probe this region through these searches at the Large Hadron Collider. And to do that, we use these two constraints that I had told you, because this analysis was done in 2017, and now we were in 2020 when we did this paper. And therefore, we use these two constraints. And we actually translated the current constraints on the heavy electroweakino searches to our parameter range. And we said that we will exclude all the points where the heavier neutralinos and the charginos are less than 390 GeV, and all the heavier neutralinos as well as the charginos have a Higgsino composition which is greater than 90%. We said such a point is disallowed because of this limit. And also a point where the neutralino and chargino are less than 650 GeV, and both of them have a substantial fraction of Vino. We said that, okay, this one rules these out. We should do better, and we are doing a better job of this recasting. And then we asked the question whether HLLHC and HELHC can probe this. And what we are able to see is that HLLHC, these blue points are within the range of discovery at HLLHC for the final state that we did consider. However, there are a whole lot of points which are still not be covered by the HLLHC searches by this particular final state. They would have been covered by a high energy LHC, but which now seems further and further distant dream. But anyhow, this is what we had performed at that time. And now we are actually keeping ourselves busy by looking at whether there are additional channels that we exist, which they do, where we can probe these orange regions, because these are these channels do not have substantial, these particular points do not have a substantial branching fraction into the trilepton and missing ET signal. I will actually now lose it, just leave it and then go further. So there is much more recent scrutiny by my friends, Melissa, the Dutch friends, and they have actually shown us that what we suspect is true, that there are many more points in the small around MZ by 2, and we were that they are still allowed by all the current constraints. They have again analyzed it in the context of electroweak, delta electroweak, and here they are saying again that the delta electroweak is smallest if the LSP is lighter than 100 GeV. So again, this is interesting. And they have also shown that there are rather large cross sections for the mass when the masses are small. So we have indeed pursuing this phenomenology right now. Now, so I have finished only the thermal part of the PMSSM. I also told you that we assumed non-thermal dark matter. And what is nice is that now, in case basically we are not insisting on the thermal dark matter, that means we allow the chi-1 knot twiddle to give large relic densities. Now, if we allow it to give large relic densities, the couplings of this chi-1 knot twiddle with the W's and the Z's and the standard matter particles are very different. And we are assuming here that some heavy modular decay, some entropy injection will reduce it to the appropriate relic density. But what is nice here is to show you that the allowed points, actually these blue points are all points that are still allowed by all the current constraints at the Large Hadron Collider and can be probed at the HLLHC. So that is rather nice. I mean, even here, there are a few points, since Gagan, who is if he is in the audience, there are quite a few points here below the neutrino flavor, and they are below the xenon 1 ton limit, reach of the direct detection experiments. But all these points can be reached at the LHC through the searches for heavier electroweakinos. That we find a very nice sign that without being bounded or limited by our theoretical biases, we can probe this entire parameter region at the Large Hadron Collider. Now we have also done some preliminary results from our newer investigations, but this I will not discuss now. I will come back to it because there is really no new information, and if I'm left, I might just come back to it. In the NMSSM, as I already said, that the superpotential is actually extended by adding one more, two more terms in the superpotential, and that gives rise to two parameters, lambda and kappa. And of course, in the supersymmetric breaking terms, A lambda and A kappa, which are the trilinear terms in the potential once you have these. So now the neutralino mass matrix actually becomes 5-dimensional, and instead of the just the 4-dimensional, and there is one more neutral fermion, which is the singlino, and the LSP now is a superposition of all the 5. The name singlino tells you that the couplings of this component to the standard model particles are precisely 0. So if your lightest supersymmetric particle is dominantly a singlino, then it's not going to interact very much with the standard model particles. But now you have a tuning parameter with which you can play, and you also have one more pseudoscalar and scalar, which are lighter than our standard model Higgs scalar, and they are still very much allowed by the LHC searches. And therefore now you have two lighter states, which are capital A1 and H1, which are available for resonant annihilation. Therefore, there are additional annihilation channels for cross, so you can increase the annihilation cross section even if your chi1 not twiddle is actually a bino singlino mixture. So here the role of earlier you had bino higgzino, now you have bino higgzino mixtures. This is a much studied subject, and there are quite a few papers that people have studied. But I think the specialty part of our analysis was that we were looking at low mass LSP, and we were looking at the connection with invisible width of the Higgs. This is just to tell you, in case some of you who know this area, that indeed there are some researchers like this, but none of them have focused on the light LSP region. And here they looked at the light LSP region, but they were looking at a constraint version of the NMSSM. We looked at the light LSP and we looked at the full NMSSM. We scanned a rather wide range of parameters in lambda and kappa, as well as the tangent beta. Now, again, our mu is restricted to 100 to 1 TeV. Now we are allowing a slightly larger values of the mu. And M1 now, you can notice, is no longer small, and it's the M2 that is actually small. And if we do this, what I'm showing you here is that after all the constraints that are allowed, so we have allowed with a lot of points where there is an annihilation through A1 and H1, which gives me allowable relic. So there is actually the relic density in units ratio of the relic density times the spin independent cross section predicted. And you see this is the relic on this axis. And if you have a yellow region, that means it produces exactly the right amount of relic. If it's green, it means that there are more than one dark matter particle, but it is not overclosing the universe. And indeed, we are able to see that in the low mass region, a whole lot of points are allowed by xenon 1 ton and xenon n ton. Even after that, there will be still points allowed. Also, what you see is that a whole lot of points which give rise to small, not so small relic are allowed at rather small masses, and they are sometimes even below the coherent neutrino scattering floor. And indeed, one needs to have new dark matter detection, direct detection experiments which will have sensitivity at these low values of the masses to be able to rule them out. But important point is, can they be probed at our colliders that we are thinking about? And here is second plot, which tells you that some of those points which are below the neutrino floor, which are below the xenon 1 ton dark matter detection constraints, these green points indeed can be probed at the International Linear Collider or at the FCCEE or at CEPC, because they predict the invisible branching ratio for the Higgs, which is about 1%, and that is way below the limit that LHC can ever reach. But these guys can actually probe these regions. Now, can this be probed at the high luminosity LHC? Again, through the final stage that we had looked at, and voila, lo and behold, you find that through the different final states that we have got, we did a very detailed analysis, and and this has been now verified, cross-checked with the experimental group's work, and we find that these regions, the green really means, if I remember right, that it can be probed at 5 sigma. This blue means that it can be sort of ruled out at 3 sigma, and this is something that remains unprobable. And there is also very nice complementarity. This region is not reachable at HLLHC, but however, correspondingly in a different channel, this region is quite reachable. So what is my general conclusion? That we have found that in NMSSM, a light LSP is very easily accommodated. This is the plot that shows this to you. Then we are able to search, it comes from the light A1 and H1, and which are actually achieved by rather low values of kappa and lambda. And somebody can ask, is that natural? And we don't have any clue as to what should be the values of kappa and lambda from any argument. So therefore, this is the way it is. And our LSP is mostly singlino, and the difficulty to search for a mixed light LSP region is now, that is why it is somewhat difficult. But we have seen that in spite of all this, we are able to search for this light LSP region. Now we want to actually do this simplified model analysis and try to understand this in the language of simplified model analysis, because here we had to work very hard to find the regions in the NMSSM parameter space which will populate these regions. So now we would like to do this in a model independent way and come back to NMSSM and study this further. Now the last 2 slides actually, that a light neutrino can also be an LSP, and you can avoid direct detection constraints here by the small Yukawa couplings of this neutrino, which is a right-handed. And now you also have an NLSP, which is tau1. You actually get the correct relic density by a freezing mechanism, or you get it by decay of long leads tau1. This is a very nice paper that Shankha Vishwarup and my collaborator Genevieve Belanger, and then also Shankha and Genevieve wrote. And there is a lot of interesting phenomenology that can be done at neutrino masses of 30 to 40 GeV. And by a comment of Vasudev, I realized that this may be also translated to mixed, some kind of asymmetric dark matter discussion. A light neutrino can also be LSP in NMSSM. And again, in that case, you can actually build specific models, and the invisible width measurements would actually constrain the picture. But this has not been looked at since 2015. But many of these scenarios will give unusual signatures. And we have actually discussed some of that in a white paper, which is now actually on the archive. I forgot to put here the number. I think I will skip my discussions on the heavy Higgs phenomenology and go directly to my conclusions that a light LSP in PMSSM is still possible. A light neutralino can be light neutralino, and mostly the H125 funnel region is what is allowed, but we are beginning to see that the Z funnel region may also be allowed. And these regions can be probed extensively and almost completely at the HLLHC. In NMSSM, a light LSP is allowed even happier, and the relic is reasonably large. Only thermal scenario has been studied, and the direct detection, LHC searches, and the invisible branching ratio, all these will offer probes of this scenario in the direct detection experiments, in the LHC searches, and in the E+T- experiments. Then in the PMSSM, which is extended with neutrino, again, there are very characteristic signals, and LHC can really throw a lot of light on the phenomenology here. As therefore, the WIMP paradigm for a light LSP in PMSSM, in NMSSM, can really be tested comprehensively at the HL and HE-LHC, at the ILC, CEP, CFCC, and direct detection experiments. Direct detection experiments which have reached at low mass neutralinos are highly desirable, and heavy Higgs decays which give very interesting signatures, such as long-lived particles at the HLLHC, is also an area of rich phenomenology. So I guess the quest continues. Thank you very much.
Thanks, Rohini, for the talk. I think the floor is open for questions. Please raise your hand. Kajadi, please go ahead. Kajadi, can you hear us? Okay, I think.
Can you hear me now?
Yes, please go ahead.
Okay. Yeah. So Rohini, thank you for the nice talk. Of course, always that is the case. Towards the beginning, you mentioned that these exclusion plots are not being made by the collaboration these days. That is not true. Even for Maria.
No, I have not seen this as what Atlas had made and which is in the PDG. That I had not seen.
Atlas and CMS both makes, and they update typically for the winter and summer conferences.
No, I have no, Kajari, you misunderstood me.
Yeah,
you misunderstood me. What I'm saying is that your exclusion for different searches are updated. What I meant was that
the second plot.
The second plot. Okay. That I think is very nice.
That is not being made.
That is not being updated. That is what I meant. Of course, you are updating.
Yeah,
I mean,
yeah.
you people are doing a lot of very important work.
No, that's what I wanted
Yeah.
to say. Yeah.
No. Clearly. I meant, and that is why I showed the corresponding plot from the paper by Ellis, okay, the master code people, where theorists have sort of reinterpreting the searches and putting those plots, because you see, the exclusions that you put are for 100% branching ratio, right?
Yeah.
They are in the simplified models.
Yeah.
And you have to recast the analysis, at least in terms of what are the predicted cross sections and what are the predicted branching ratios, and fold that in with your results
Exactly.
to see which models get ruled out. And I find that that is a sort of a very nice exercise, which was done by at that time by Atlas. And I hope that you guys can do this, because whatever we do, still we are only reinterpreting your results, and we might be not correctly interpreting everything you say, you know. So you are the best people right now, even now, to tell us whether, you know, because in some sense that gives you at one shot that even if you are saying that my, you know, general stop mass limit is now very close to 800, 750 GeV. But then you see that there exists 30-40% of the models that you look at, you say that the stop mass of 500 GeV may still be allowed. So that actually is a kind of a very useful information for most of the people who are looking just at the models.
Yeah,
that's what I meant. Okay.
Okay.
So is this clear?
Yeah. I understood. Okay. I know that you are keeping track of things, definitely. I have a second question.
Yeah.
I wanted to check with you. You know that recently both Atlas and CMS has come out with the limits on the invisible Higgs.
Yeah.
Roughly around 10-11%.
Yeah. So this I had 13%, but now it's 11%.
So how much it will change actually?
As I told you, I put my analysis wouldn't change at all, actually.
Okay.
And the reason is, I'll give you the reason for that. The reason is that in supersymmetry, there is an indirect constraint that comes by demanding that you satisfy all the Higgs rates, you know, observed standard model.
Yeah, that is true.
And that indirect constraint on the invisible branching ratio is something like 10%. So therefore, now the direct constraint and the indirect constraint are almost at the same level.
Yeah.
And therefore, since we anyway put those constraints that the Higgs should be as you have seen it.
Yeah.
And that constraint already rules out the regions of the parameter space where the invisible branching would have been higher than, let's say, 11%. So therefore, I am much more happier putting the constraint from the direct observation, because that is kind of free of interpretations.
Sure.
And therefore, but now, as you know very well, from the 11, one might go down to 8 to 7%. But
8 to 7 was the expected value.
Yeah, exactly. I mean, even our old paper, myself, Manoranjan, I mean, the paper that we wrote was very old. But after that, Manoranjan, myself, we wrote the paper for electroboson fusion also. And there we had come up with something like 10%. And
our first paper with Zeppenfield, that gave a limit of about 13% or so.
Yeah. So, so it's been, I don't think this is going to change. I mean, 10% is going to be the
ballpark number.
Ballpark that we will ever reach at the LHC, I feel. Unless something very clever is done for handling the tagging of the jets.
Okay, thank you.
You know it better than me, so.
Thank you.
Nishita?
Yeah, hi. Thanks for the nice talk, and it was really nice to see the overview of the regions that are still allowed. I'm just worried about one small thing. So if I understood what you're doing correctly, for the PMSSM, you require a Higgsino admixture, and for the NMSSM, you require a Vino admixture.
Singlino.
Singlino and Vino, right?
No, not Vino. Singlino and Higgsino and Vino.
Okay. Anyway, so the point was that you require a small mu parameter to get the relic density correctly. So I would expect that you almost always have a very light chargino in your spectrum. And you are only ruling out charginos if they have 90% we know or 90%.
Oh, no. That okay. That is for that we did only for PMSSM.
I see.
For NMSSM, we actually did the full-fledged chargino and neutralino analysis.
Okay.
And we implemented the complete constraints.
Okay, that's good.
Because there was a gap of about 4 years between the two analyses. When we did the first analysis, we were not so very well equipped to do the chargino neutralino searches and implement them.
Right.
And right now we are doing something even stricter, which you will like. We are now implementing models.
Okay.
I mean, this thing about ruling out with branching ratios was a poor man's way of implementing, avoiding models.
Yeah.
And what is nice, actually, I can tell you this, that there is a lot of, we are not doing too badly with these constraints which we put just on branching ratio. Now we are but our comparisons are not complete. That's why I did not quite show those plots. But that's
I was just worried because with this simple analysis, you seem to be allowing, say, 110 GV chargino, that may be 50-50, higgses.
No.
Clearly should have been.
No. This is, and anyway, LEP limit is always imposed, right?
That's 103, but
103 is always imposed. That is always imposed. But no, more than that.
A bit,
no, more than that. We are doing it, so don't worry.
Okay, good.
Yeah. Actually, many of those points will also be already not allowed because of the neutralino limits. Because there is a correlation to some extent between what is allowed in neutralinos and what is allowed in charginos.
You mean just by MET searches?
Just by MET, exactly. Just by MET searches. So that, but your point is well taken, but luckily, I can show you the mu-M2 plots if you want, and that would put...
yeah, sure. Because it's just that it seems very low mass.
No, but we have investigated and have looked at it as the mu-M2 plot also.
Okay, great.
You have kind of asked the question which we investigated while we were putting out this paper. So clearly we looked at that. And that's a valid worry. I will definitely agree with you.
Okay, Amol has a question. Amol?
Hi. I think if I heard you correctly, at some point of time you made a statement that if you are allowed to inject entropy at some point of time, then you can get over the relic density constraints. So one question, of course, can you elaborate on this, the physical argument? And second is, you of course showed various other ways, in your later talk about how you get around this. And do some of those ways correspond to injecting entropy?
No, both those ways are actually not injecting entropy.
Okay, fine. So good. Now can you tell us this argument?
No, the injecting entropy is that then some heavy modulus, basically decays into some final states. That's going to add to the entropy, right?
Yes.
And then since we are actually, and there is actually some amount of work that has been done in this context by Fernando Quevedo and also our friend Maharana, young Maharana, I forget his name. And also some work was done by Utpal, where they constructed. Now the point is, however, I should give a big disclaimer that these usually correspond, actual mechanisms which have been constructed, usually correspond to a large mass Higgs. The explicit examples that people have constructed. So in that sense, it's not my mass region, nobody has demonstrated ever that this can actually be done. But I am just saying that, see, this is a kind of approach that I'm taking, that I don't know enough about cosmology. So can I sort of indirectly, because the couplings in that region are very different, which gives you a large density. The couplings are extremely different. So can the collider actually tell you that, even if you are very clever and thought of 20 different scenarios to make the relic right, it's not going to work because colliders can probe it and tell you whether you're right or wrong. That was the approach that I was kind of taking.
Oh, so this of course I understand. So if I understand you correctly, what you mean is, if you are not getting enough relic density, okay, then you can get the remaining by decay of some heavy particles. Is that correct?
No, there are two ways.
What
If
about
you're
the
not
other
getting
way
enough relic density, then the freeze-in gives you. So there I don't have to think of this in dumping of entropy. What happens is that if I'm getting too much relic, so the particle has frozen, I got too much relic.
Okay.
But then some additional particle decayed. Then all I can do at the end of the day in cosmology is calculate the number to entropy ratio.
Okay.
And if the entropy at some point in the early life of the universe has increased suddenly, there is a jump in the entropy.
Okay.
The relic didn't change, but the
Denominator.
relic to entropy ratio changed. And finally, what I measure is relic to entropy ratio.
Thanks.
If I may, yeah, you are talking about the reheating temperature lower than the freezing temperature, right? This is when the moduli and inflaton.
That is exactly the point. That's why I told him that the freezing is not equivalent to, I think that was the question that Amol had. And thanks for providing the keyword, but this is what I mean. So here it was a very stupid man's question, so to say, that I don't know, I'm not very, no understanding of the early cosmology. There are different hypotheses. Some hypotheses which actually can, in a framework with certain parameters of supersymmetric moduli and so on and so forth, can actually achieve this. They have shown that you produce a lot of relic and then the values of the parameters are such that the modular decay would inject right amount of entropy, such that even if your relic was above by factors of thousands, you would dilute it. So when you're saying dilution, it's like huge dilution. Now for a light mass, I don't think that has been demonstrated. This can be done only for a heavy neutralino. But then I kind of take a poor man's approach that let me see if I can probe this region at the collider. Since that's the only machine we have got, and that's the only machine we are likely to have for a while, might as well utilize it as much as we can. So sort of a very pragmatic kind of approach. And I would like to do the same for NMSSM, for example, so that we are not giving up these ideas because of our biases. That is essentially that essentially it's saying that let's rule it out completely as we can. And that's the approach, at least, that I have taken in this entire line of investigation.
Okay, Utpal has a question. Utpal.
Can you hear me?
Yes, Utpal.
Yeah, very nice talk. And I enjoyed the whole thing. I mean, lot of things you have mentioned, and it was very comprehensive. I have some query regarding what if the Higgs discovered is the second Higgs, not the smaller Higgs. So in that scenario, do you have any update?
Okay, now actually it's a very good question that you have asked. And in fact, in the NMSSM, a major region of my parameter space is such that the observed Higgs is the second lightest Higgs.
Now, what about
indeed,
the PMSSM?
I have H1 and A1.
PMSSM? What about the PMSSM?
PMSSM, no.
What is the latest standing?
No, I haven't. At least our analysis didn't support such regions.
Okay.
But in NMSSM, actually, it is precisely this that allowed us the additional annihilation channels. I know there are some people who still think that what we have seen is the... No, I mean, I think these issues are interesting and needs to be surveyed with a sort of an open mind. And maybe precision Higgs measurements will tell us something otherwise. I don't know.
Okay.
I mean, that's where I think we need a ILC or any plus minus machine for that matter.
Okay. Thank you.
Thanks for your question.
Any more question? All right. I don't think there is any more question. Really, thanks a lot for both the talk. It was very energetic talks. We enjoyed it.
as long as you did. That's good.
Here is also Shru. So thank you, and all of us.
Okay. So bye-bye, everybody.
Bye, everybody.
Bye, Kajari. Take care.
Thank you.
Bye.